Limits? Continuity? Oh, I feel like I'm lost with all these type of terms.
Hey Wendy, you look so troubled. Everything okay?
Not really. I'm so confused about continuity and the exams tomorrow.
Continuity, huh? Have you checked out bmatalino.com? They make math fun.
bmatalino.com?
Yes, let's take a look.
Welcome to Mathalino, where math is an adventure. Today, we're tackling word problems involving limit loss and continuity. But think about it like a bridge. Can you walk across it without any jumps or breaks? Let's find out. This very moment, we are going to discuss solving real-world problems involving continuity and limit loss. Before we delve deeper about it, let me ask you something. Have you ever wondered what would happen if your favorite roller coaster suddenly just stopped? Or if a road just disappeared mid ride? Or what exactly are limits, laws, and continuity?
Well, let's talk about limit laws, the secret weapon that help us simplify complex math functions and figure out what happens when we approach a certain point. Limit laws allow us to compute limits by breaking down complex expression into simple pieces and then evaluating the limit one piece at a time. Think of it like this. If you had to solve a huge complicated puzzle, wouldn't you break it down into smaller, easier pieces? Limit laws let us do exactly that.
Since Wendy have introduced to us what is a limit law, now we will tackle about the different types of limit laws that will help us break down the limits into simpler ones. First up, the sum and difference law. It says this limit of a sum or difference is just the sum or difference of the individual limits. So we will just split the limit into two easier limits, solve each, and then added them together. Same goes for subtraction. Okay, so next is the constant multiple law. If you have a constant multiplied by a function, you can pull the constant out of the limit. So you will just took the numerical coefficient outside the limit, making it simpler. Now, the product and quotient laws. It is similar to the sum and difference law. The limit of a product is the product of the limits, and the limit of a quotient is the quotient of the limits. But with one very important condition for quotients, the limit of the bottom part, the denominator, cannot be 0. So the power and root laws are similar. The limit of a function with a power is just the limit of the function with a power outside the limit, and the limit of a root follows the same law. And finally, the two easy ones. It is the constant identity law. The limit of a constant is just the constant, and the limit of x as x approaches a is just a. But what about continuity? Can you elaborate it more, Daniel?
Here's the thing. Continuity is like the smooth roller coaster ride where you're just cruising along. No bumps, no sudden drops, just nice smooth flow. A function is continuous if, when you plot it on a graph, there are no breaks or interruptions. Also, a function f of x is continuous at x equals to c. And in case you forgot, the limit laws help define the continuity. Alright engineers, we've got a challenge in our hands. Imagine you're designing a bridge and you've got a support structure that's modeled by this function f of x minus 3x plus 2 over x squared minus 4. This function represents the position along the base of the bridge in meters. Now, your tasks are clear. You need to find the limit using limit laws and interpret the result. If the limit is a finite value, the structure is stable. If the limit does not exist or miscalculated, incorrect force distribution could lead to structural failure or collapse.
So, engineers, we've got a classic case of a limit problem. And the first thing we usually try is direct substitution. So let's plug in x is equals to 2 straight into the function of x cubed minus 3x plus 2 over x squared minus 4. So what happens if we substitute x is equals to 2? It will turn into 2 to the power of 3 minus 3 times 2 plus 2 over 2 squared minus 4. 2 to the power of 3 becomes 8. Negative 3 times 2 turns into negative 6. 2 to the power of 2 turns into 4. 8 minus 6 plus 2 becomes 4. 4 minus 4 becomes 0. Since we get 0 as the denominator, the function becomes undefined or does not exist. Now let's tackle this problem like true engineers. When direct substitution fails, we often try factoring. Let's break it down. First, you must factor the numerator. The numerator is x cubed minus 3x plus 2. We know that x is equals to 2 makes the numerator 0. So x minus 2 must be a factor. Now let's factor it out. We'll divide x cubed minus 3x plus 2. Next, you must factor the denominator x squared minus 4. Now this is a difference of square, so we can factor it as x cubed minus 4 is equals to quantity x minus 2 and quantity x plus 2. Got it? So now our expression looks like this. Now look at that. We've got x minus 2 in both numerator and the denominator. Since x is approaching 2 but not equal to 2, we can cancel this out. So we're left with x squared plus 2x minus 1 over x plus 2. Alright, now comes the fun part, evaluating the limit. This time, we can substitute x is equal to 2 directly into our simplified expression. Now, it becomes 2 to the power of 2 plus 2 times 2 minus 1 over 2 plus 2. 2 to the power of 2 becomes 4. 2 multiplied by 2 becomes 4. So we have 4 plus 4 minus 1. And on the denominator, it's 2 plus 2 is equals to 4. Now 4 plus 4 minus 1 becomes 7. And since the denominator is 4, we have 7 over 4. So, the limit of this expression as x approaches to 2 is 7 over 4. What do you think? Is the structure stable or is something going wrong? But if the limit didn't exist, or if we got something like infinity or undefined, that would be a red flag. It could mean that the force distribution at that point is unstable, and the structure might fail.
Oh, thanks for watching, and until next time, keep on solving, keep on learning, and stay matalino. Bye-bye!